Okay, so let's see another proposition that has to do with the last one in the last video. Okay, let's consider that k is a positive integer and phi, let's see, k and we will say that phi k x more than or equal than 1 for any x in AB closed with 5 of x prime monotonic in the case k equals 1. Then integral AB ei lambda phi x dx absolute value less than or equal than a constant say k lambda minus 1 over k, and ck is independent of AB. Okay, so let's prove this for k equal to 1, and and then we will have to make an induction to see for the other case. Okay, so k equals to 1. Then so we have the integral AB ei lambda phi of x dx is equal to, okay, so we integrate by parts. Ei lambda phi b ei lambda phi prime b minus ei lambda phi a over I lambda phi prime a minus 1 I lambda ab integral ei lambda phi x dx 1 over phi prime of x. Okay, it's an I, and okay, so if we now we put all this in an absolute value, ABE ei lambda, okay, phi of x dx will be less or equal than, okay, so now we can use the that is less than 1 absolute value of lambda phi prime b plus 1 over lambda phi prime a plus 1 over lambda AB dx 1 phi prime x dx. Okay, so I see now that I'm missing a dx here. Okay, and this should be also an absolute value because it came from inside the integral. And so this will be less than equal than, okay, now we take a common factor of 1 over lambda, okay, and this will be multiplied by 1 over absolute value of a f phi prime a plus 1 over phi prime b, okay, will be plus 1 absolute value of 1 over phi prime a minus 1 over phi prime b. Okay, and I would close the parentheses. Okay, recall that phi prime is monotonic in AB, which that means that d over dx of 1 over phi prime has a constant sign. Okay, and so we transform this, or let's say this, ddx, into this, resolving the integral, and so we can say that this is equal to 2 over absolute value of lambda and the maximum of 1 over phi a, phi prime a, and 1 over phi prime b. Okay, because we just have to decide which one is the biggest of the two, and we just take the one and sum it. And okay, 2 over lambda. Okay, and phi prime is greater or equal than 1, so then we can say that this is less or equal than 2 over lambda. This will be for k equals 1. Okay, the absolute value appeared from inside the integral, but I could have taken it without the absolute value. I see. Okay, then one would have to make something similar for k greater than 1 by induction. I'm not going to do it, but one can make you can bound the integral just by using the hypothesis that 5k derivative um, is greater than or equal than 1. Using that, one can prove by induction the bound ck lambda to the minus 1 over k. Okay, so under the same hypothesis as the proposition that we just looked over, one could have a corollary. Bundle Corput is to whom it's attributed. Assuming the same hypothesis as we just saw, the corollary says that the absolute value of the integral of ei lambda phi of x f of x dx is less than or equal than ck lambda minus 1k and norm infinity of f plus norm 1 of f prime. Okay, and ck is independent of ab. Okay, so the proof this will be, okay, we define g of x equals to the integral between a and x e I lambda phi I dy okay, and of what because of what we just saw, we have that gx absolute value is less than equal than ck lambda minus 1k. Okay, so so now we will put absolute value of ab e I lambda phi f dx. This will be equal to absolute value of integral ab g prime f dx. G prime just going to be ei lambda phi, and so this will be less than equal than the absolute value of let's say gf. We are using now integration by parts. Absolute value, this will be in ab plus, let's put it here, plus, and now is the integral in ab of g f prime dx, and I'm missing the absolute value here and here. So we just integrate by parts, and now we can use that gx is less than equal than ck lambda minus 1k, and so we will have this bound for this g and this other g. So we can put here lambda minus 1k, and then we will bound this f with the norm infinity, and this one will be with the norm 1, and we obtain the results. And now I'm just going to write another proposition, not going to prove it. Let beta in interval 0, 1/2, and my beta of x is going to be the following oscillatory integral. Let's write it here. I beta x is equal to the integral minus infinity infinity e I x, and now nu plus nu the third absolute value of nu beta d nu. So we have that. Then I beta will be in L infinity of R.